diagram. It's a good time to start. So, hey everybody, today we have John Kolesar today, and he'll be talking to us about zero knowledge, and he's from Yale, and he'll be talking about zero knowledge proofs for SMT theorems and regular expression equivalence. And now he'll say some things you cannot see on the first slide.
Yes. Thank you for the introduction. My name is John Kolesar. I'm a fifth-year PhD student at Yale, advised by Ruzik and Piskach. And today, I'll be talking to you about zero-knowledge proofs for SMT theorems and regular expression equivalence. This is some research that combines two separate areas, formal verification and cryptography. If you're not familiar with it, formal verification is the task of proving mathematically that a program satisfies some safety property, such as memory safety or the absence of overflow errors. There are well-established tools from existing work called SMT solvers, where SMT stands for satisfiability modulo theories, that can do this task automatically. To use an SMT solver to verify a program, we can express the safety property of interest as a logical formula, and then ask the solver to produce a proof that the negation of that formula is unsatisfiable. Cryptography enters the picture when we want to convince other parties that a program safety proof is valid without revealing the proof or the program, in case there's some sensitive intellectual property in the code that we want to keep secret from those other parties. To set your expectations, here's the ordinary pipeline for non-cryptographic program verification, where everything is public. We have a specification of the property that we want our program to uphold, and we have the program itself written in an ordinary language. And from the program and the specification, we create a logical formula that encodes what it means for the program to uphold that property. We then have a proof of the formula, and we can see at the end that the proof is correct. Here's what we want instead for zero-knowledge verification. The specification is still public, and we can still see at the end that the proof is correct, but the proof is private, the formula is private, and the starting program is private too. For this research, we're interested specifically in this part of the pipeline, going from the formula to the proof to the correctness result at the end. The reason why we want zero-knowledge verification is that it can help with the task of safety auditing for proprietary software. It's common for government agencies and private companies to require software from external developers to undergo a safety audit before being deployed. And the standard way that happens now is that the developers simply need to hand over their source code to the auditors, who then inspect the code and run it. The trouble with that approach is that the developers may not entirely trust the auditors. They may not want to expose any sensitive IP in that code, even if it's just for the purpose of testing. A better alternative would be to allow the developers to provide a zero-knowledge proof of their program's correctness so they can convince the auditors that the program is safe without revealing the code directly. If you're not familiar with zero-knowledge proofs, a zero-knowledge protocol, or ZK protocol for short, is a method of communication between two parties known as the prover and the verifier. In a ZK protocol, the prover convinces the verifier that it knows some secret without revealing the evidence for the secret. The quintessential example of a ZK protocol is the Coke-Pepsi taste test, where the prover has some secret knowledge about how to distinguish Coke and Pepsi by taste, and the verifier wants to confirm that. So for the protocol, the verifier fills a cup with either Coke or Pepsi secretly, and then asks the prover to say what it is. If the prover gives the wrong answer, then the verifier knows the prover was lying. If the prover gives the right answer, it's possible that was just luck since there are only two options. But if the two repeat this process enough times, and the prover keeps giving the right answer every time, the verifier eventually will become convinced that the prover really can distinguish Coke and Pepsi. Importantly, the verifier never learns how the prover is doing it, and running further executions of the protocol doesn't bring the verifier closer to getting that information. That's the essence of zero-knowledge proofs. By the way, I should point out at this point that I'm using the word proof in two different senses here. Zero-knowledge proofs and logical proofs are two different things. And for our purposes, we want to provide a ZK proof about the existence of a logical proof. There has been some prior work in the domain of ZK verification, but existing protocols aren't entirely adequate for proving program safety because most older ones demonstrate the existence of a witness that satisfies a formula rather than showing the existence of a proof that a formula is not satisfiable. We care about the distinction between satisfiability and unsatisfiability because for program safety properties, we usually want to confirm the absence of bad execution paths rather than confirming the presence of good ones. There is one older ZK protocol for encoding proofs, namely ZKUnsat, but it handles only resolution proofs in pure Boolean logic. We want to be able to support first-order theories like equality with uninterpreted functions and linear integer arithmetic so we can give a more accurate picture of how programs behave. Also, there are general-purpose ZK protocols that can model the execution of arbitrary programs in zero-knowledge, but they're very inefficient, and we would prefer to have something that's specialized to the task of proof validation. To address that need, we introduce ZKSMT, a VM for proving SMT theorems in zero-knowledge. With ZKSMT, the prover can demonstrate that it possesses a proof that some logical formula is unsatisfiable without revealing the proof or the formula itself. Let's take a look at how ZKSMT works. Our starting point for ZKSMT is this: the output from an SMT solver that confirms that some logical formula is not satisfiable. We want to turn this proof certificate into something that can be validated in zero-knowledge. Note that we're not searching for this proof inside our ZK VM. We construct it up front and then turn it into something that can be validated in ZK. Now, the format of this proof is ultimately a tree. We have proof steps that take other steps' conclusions as premises and produce new conclusions that later steps can use in turn for their own premises. The obvious thing to do to hide the details of this proof would be to hide the formulas manipulated at each step. But if we hide only those formulas and we don't hide the connections between proof steps, we're still leaking a lot of information about the proof. And we run the risk that the verifier could reverse engineer what these formulas are just from seeing the connections between different steps. We need to rethink the structure of our proofs instead. So we can have a linear proof format where we treat our steps like instructions in an assembly program. It's still the case that proof steps take other steps' conclusions as premises, but instead of having an explicit tree, we have these premise pointers that connect different proof steps to each other. And when we switch to having our proof steps in a table like this, we can hide the step IDs, the conclusions of each step, and also the premise pointers, which indicate the connections between different proof steps. On top of that, we can shuffle the order of our proof steps to hide any information that could be gained from their relative ordering. This new proof structure is part of a larger proof format that we call our proof checking VM. Yes?
So you switched from the tree to this linear structure because are you trying to give the proofs step by step or?
Yes, the ultimate goal is to give out these proofs step by step.
I see. You're not treating it the whole thing as one unit and
no,
at once.
No, well, we validate the whole proof by breaking it up into these little units, which are easily validated in ZK.
I see. And you want to hide the structure because that leaks information.
Yes, the structure leaks information.
I see. And why don't you do it the whole thing at once? Is it too inefficient?
Well, because hiding tree structures of arbitrary depth and complexity is a hard thing to do in zero knowledge because you need to apply a lot of padding to cover up all the different possible tree shapes. Mm-hmm. But if we have just a linear table, then hiding the shape of it is easy to do because the shape is just the number of rows in the table. So every individual thing can be verified in a simple way. Yes?
Are you not hiding the rules?
Well, hiding the rules requires a bit more work because in order to check a proof rule, you need to give some information about what rule is being checked. But if you shuffle the order of the proof steps, it's possible to showing what rule is being used for an individual step. It doesn't leak information about the connections between proof steps because we shuffle them and hide those premise pointers.
Yeah, but you still need the set.
Yeah, yes, it does show the which rules are used within the proof.
Yeah. So how do you break them into some units?
Well, we break them into units. Well, we do that.
For example, how you break it to set a unit?
Well, the proof from the solver comes already split into distinct proof steps, and we're just linearizing that into the table like you see here. So SMT solver proof certificates are already based on a system that's similar to this, but the trouble is that it has the tree format, and we're just taking proof steps that are like those and putting them in a linear format instead. So some of this discretization of proofs is already done for us up front. Yes. Yes.
Sorry, so just to clarify this setting, so the formula that you're trying to prove is public.
Well, the formula is private too. So this ZK protocol itself doesn't force you to reveal the starting formula. It is possible to reveal part or all of that starting formula as a way of grounding the ZK proof as part of some larger structure. But the ZK protocol itself doesn't force you to reveal what formula you're proving unsatisfiable. So yes, this proof structure is part of our larger proof format that we call our proof checking VM, which you can see here. The rationale behind this design is that we want to split our proofs into discrete parts that can be checked independently of each other so we can hide the structure of our proofs. And within our proof VM, we have the step table that you saw on the previous slide. That's the list of all proof steps laid out like an assembly program. And we also have the expression table, which is a list of all the terms and formulas in a proof stored as abstract syntax tree nodes. Along with those, we have a list of checking instructions, which are the functions for confirming that individual proof rules are applied correctly for proof steps. In the execution of ZKSMT, the verifier iterates over all the steps in the step table one by one, confirming that each step is valid in isolation. And after the verifier does that and applies some extra high-level checks to the proof as a whole, that confirms that the entire proof is valid without leaking what the structure of the proof is. So let's talk about how exactly we check these proof steps within ZKSMT. As I mentioned before, a proof step has premises, a conclusion, and a proof rule, where premises point back to the conclusions of earlier proof steps, and the proof rule tells us how to check whether that step is valid. For instance, for step number 3 here, we're using the proof rule called eq_split and taking the conclusion of step number 1 as a premise. We're deriving the conclusion 2x is greater than or equal to 1 and 2x is less than or equal to 1 from the premise 2x equals 1. To see whether this is a valid derivation, we apply the corresponding checking instruction for eq_split to this step. The way that checking instructions work is that every proof rule within our calculus of rules accepts premises and conclusions of some predefined generic pattern. And the checking instruction for a rule confirms that specific uses of that rule align with the generic form of the rule. For eq_split, our generic form is that we derive a conjunction of greater than or equal and less than or equal from an equality premise where the left and right child match between all 3 of those. Let's take a look at that in action. Starting from our step ID for the step we're examining, we go into the step table to fetch the conclusion ID for the conclusion formula and also the ID of our premise. With that, we can fetch the conclusion ID of the premise as well. And once we have those 2 conclusion IDs, we go into the expression table to fetch the formulas for our premise and conclusion. The conclusion formula has child pointers for its 2 subparts, so we can retrieve those from the expression table as well. Once we've fetched everything we need, we perform pattern matching on these AST nodes and their children to confirm that they match the generic form of eq_split. So we confirm that we have an equality node here, an and node there, and greater than or less than nodes as children of the and node. And we confirm that this left child matches those 2 left children, and that this right child matches the right children of the greater than and less than nodes. Note that we never actually need to fetch these red nodes from our ZK memory. We just need to do pointer equality checks using the child pointers from their parents. And that means that we never even need to consider these green nodes that are beneath the multiplications. If we have pointer equality for their parents, they have to be equal as well. In general, we set up our calculus of proof rules so that we don't need to do AST traversals of arbitrary depth. We just do pattern matching at the top level of the expressions that we're considering. Now, this on its own isn't a ZK proof. If you want to turn proofs like these into ZK proofs, we need to apply some cryptographic techniques. We hide the values manipulated by each step in our proofs to make different uses of the same proof rule indistinguishable from each other. We achieve this using a cryptographic technique called commitment to hide the integer values in our proofs. When we commit an integer, that means we map it to an element of a special finite field such that recovering an integer from its commitment is not computationally feasible. You can think of it as working like a hash function in that regard, although the analogy isn't perfect. Within our commitment scheme, we can add and multiply committed integers to produce new committed integers without revealing their values to the verifier. And we can also perform comparison operations on them, including equality, greater than, and less than operations. The reason why this is important is that when we're validating a proof in ZK, the verifier needs to be able to see that all the different steps in a proof are consistent with each other. And unlike plain old encryption, commitment binds the prover to a specific underlying value for what the hidden integer is. That means that the prover can't treat a committed integer as having different values at different times. If we have a committed 6 within our proof, it needs to behave as a 6 every time it's used, even though the verifier can't see that it's supposed to be a 6. But if the prover tries to pretend that this committed 6 is actually a 7, the verifier will be able to see that that's fake. Now that covers the information that we want the verifier to have, but there's also some information we don't want the verifier to have. We don't want the verifier to be able to do extra operations on these committed integers to be able to recover more information about our ZK proof than is necessary. With our commitment scheme, the verifier is only able to see the results of these operations on committed integers when the prover provides auxiliary inputs that make those results visible to the verifier. That means the verifier can see whatever information we want to disclose to confirm that a proof step is valid, but the verifier can't do extra operations on these committed integers behind the prover's back. Also, it's possible for the same integer to be committed in different ways. So for instance, 2 different commitments of 6 within a proof are not immediately recognizable as equal from the verifier's perspective. That's where the hash function analogy breaks down. And that's a safeguard against doing frequency analysis on committed integers. The verifier can only see that 2 committed 6s are equal if the prover provides the auxiliary input for that. So now we've talked about our methods for handling individual integers. Let's talk about how we represent terms and formulas in our ZK proofs. We represent our terms and formulas as abstract syntax trees, where every AST node is a row in the expression table that I mentioned before. And nodes in this table store pointers to their immediate children within the table. For instance, in row 11, we have a less than or equal node that's pointing to rows 7 and 8, where its children are. The numerical values in this table are all committed, so the verifier can't see what they are. And more importantly, we support oblivious indexing for this table. That means that the verifier can use a committed integer index to fetch a row of this table without learning what the value of that index is. That's another safeguard against the verifier doing frequency analysis for our ZK proofs. Sometimes we need to manipulate lists in our proofs. And when we have lists, we pad all of them to be the same length. And we set up our checking instructions for rules that scan lists so that the verifier can't tell whether a list entry is padding or a real value.
When you say oblivious indexing, it's going to be like you have some kind of aggregation scheme and then you're comparing.
Sorry, could you repeat that?
So how do you do your oblivious index?
So what works is we have an array in ZK where the verifier can use a committed index to retrieve an entry from that array, receive an entry from that array without learning what the value of the committed index is. So
how would you do that?
It's a technique from existing work. So,
Yeah, so maybe
Usually it's going to be like this aggregation scheme.
yeah. So I mean, one way to do that is just to do like a mux over the entire thing, but that's not what they do. So there is this. So I think the zero knowledge scheme that they use like one of those volley based schemes.
yes, it's a vol based ZK scheme.
Yeah, and there's a paper of like Rafi and Shao where they show how to do like random access, which at low amortized cost, into a list in a vol-based scheme. It uses some like sort of like shuffling and subtracting, like you prove that you know shuffle. It's a pretty cool trick.
It's going to be like proving shuffling.
You don't prove shuffle, so essentially it's pretty efficient. Essentially, you can do it at like pretty low overhead. It's not like linear overhead in the list's length. It's about like logarithmic overhead in the list length.
Yes, the amortized
I can
cost.
send you the paper if you.
Yes, the amortized cost of list indexing is linear in the width of the entries, but it's independent of the number of rows in the table. And so things get more interesting for lists when we need to confirm that 2 lists are equivalent when viewed as multisets. That means that the order of elements in those lists is irrelevant, but the multiplicities of those elements matter. We want to be able to check that in linear time in zero knowledge. To compare two lists as multisets, we can interpret the committed integers in each list as roots of a polynomial, and then evaluate those two private polynomials at the same public random point. If we get the same result for both, then that means with high probability that those two polynomials are equal everywhere. That's a result known as the Schwartz-Zippel lemma. Let's look at an illustration of this in action to see how it works. With the proof rule, resolution, which is our main workhorse for Boolean reasoning within ZKSMT. Resolution is a proof rule that combines two disjunctions to produce a new disjunction that contains elements from the premises. The two premise disjunctions have to have a pivot value in common, which is Z here, where the negative version appears in one premise and the positive version appears in the other. The conclusion of resolution doesn't contain either copy of the pivot, but it does contain all other disjuncts from those premises. And within a proof, we use resolution repeatedly to work our way down from large disjunctions to small ones. This application of resolution that you see here is valid if this multiset equivalence holds. We turn our two premises into multisets, and on the right-hand side, we have the conclusion as a multiset, along with positive and negative copies of the pivot. We can turn this multiset equivalence check into a polynomial equivalence check by replacing all those variables with numbers, and then introducing a new polynomial variable x, as you can see here. If we plug in the value of 6 for x, we reduce both of these sides down to -60. And since we got the same result for both, that means with high probability that these two polynomials are the same. And since we have a bijective mapping from these polynomials back to our starting multisets, that means with high probability that this application of resolution is valid as well. Now we've discussed our techniques for dealing with individual proof rules. Let's talk about our techniques for hiding the larger structure of a proof. Our main technique for hiding the structure of a proof is that we check proof steps out of order relative to what their real underlying logical order is. What the verifier covers over the course of iterating over the step table is shuffled relative to what the real logical order of those steps is. We can do that because we set up our calculus of proof rules so that every proof step can be validated in isolation, independent of the others, without leaking connections to those other steps. Also, all of our proof rules are checkable in either constant or linear time, so we don't need to apply excessive padding to hide what they're doing. On top of that, we use committed step IDs to ensure that every step in a proof is checked exactly once, and that there are no cyclic derivations in our proofs. The check for the absence of cycles appears on lines 14 and 15. Every step has a numerical ID, and if a step has premises, the IDs of those premises need to be strictly lower than the ID of the step itself. If that holds for every step, that's sufficient to confirm that there are no cycles. The check that every step is validated once appears on line 17. It's a multi-set equality check between the list of all step IDs that we've validated so far and the list of all numbers from 0 to pi-1, where pi is the total number of proof steps. Now let's talk about our evaluation for ZKSMT. For the main part of our evaluation, we use ZKSMT to validate proofs of theorems from the Boogie verification toolchain and also some performance-intensive benchmarks from an older tool known as the Wisconsin Safety Analyzer. What we found in our running time results is that ZKSMT generally scales linearly as the number of proof steps increases in these SMT proofs. The slowest Boogie benchmark takes about 40 seconds, but most of them are quicker and take 10 seconds or less.
How much do they take without cryptography?
Well, it's very quick, fraction of a second. The time cost of validating these proofs comes almost entirely from the cryptographic operations rather than the intrinsic logic of validating these proofs themselves. Now,
sorry, I mean, what's the overhead of cryptography in terms of proving time?
Well, almost
you're going to show that, but
almost all of the time cost comes from the cryptographic operations. Now,
so is it like 1,000x? Is it like 1,000,000x? Is it like 10x?
I don't. Well, I have the results for a different part, not for this one specifically, but it's a huge difference, multiple orders of magnitude. It is at least 1,000 times faster to do it without the cryptographic operations.
Okay. Maybe another question, because I don't actually know. Maybe some of the PL people know what these benchmarks are, but I don't. Like, how close are these benchmarks say I am willing to spend like 40 seconds or even a couple of minutes like proving these statements, like can I prove statements about like actual programs? Or
Yeah.
is this
Yes.
really small?
So yes, the boogie benchmarks are derived from verification problems for realistic programs. And so the boogie benchmarks are relatively on the small side, but the Wisconsin safety analyzer benchmarks are extra large ones that are super big. The largest one that we validate successfully actually consists of about 200,000 steps and takes 3 hours to validate. So those are the big ones that we can handle.
So big?
100,000 steps. It's on the order of things, it's the smaller side of what proofs can get to, but 3 hours is a significant time to check. But of course, you're doing the cryptography.
Yes.
Yeah.
Most proofs will probably take under a minute to check for a lot of standard benchmarks, industry applications. If you get into large math problems, you get like terabyte, petabyte size.
Oh, yeah,
Those take forever to check, but these are probably no more than a gigabyte.
Right. You wouldn't try to prove this stuff. I was just
So
wondering.
like, yes, this is a significant overhead from what you would get without running the cryptography, but like, the point is that you do get the cryptography.
Right. Yeah. Oh, we can talk more after. Sorry.
Okay, was there a follow-up question?
No. Yeah.
So that covers the main part of our evaluation. For the second part of our evaluation, we looked at how the running times of individual rule checkers within ZKSMT scale relative to the size of a proof. Note that we can split proof size into multiple distinct metrics, like the total number of steps in a proof, the size of the expression table, and also the maximum size of individual lists within our proofs, which we call alpha. The most significant one of these is alpha, as you can see in the top right. The running times for individual rule checkers scale linearly as it goes up, and this makes sense because list scanning and fetching from our ZK read-only memory are both O of alpha operations. On the other hand, the size of the expression table is largely irrelevant, as you can see in the bottom right. For the third part of our evaluation, we did a baseline comparison of ZKSMT against cheesecloth, which is a general purpose ZK protocol for executing LLVM code. Returning to our boogie benchmarks from before, we can translate the proof validation process for those benchmarks into a ZK program that cheesecloth can execute. And once we have those ZK programs in hand, we can give a conservative estimate of what the running time of cheesecloth would be based on the program's cycle count. And you can see the results here. At best, cheesecloth is more than 1,000 times slower than ZKSMT is, and at worst, it's more than 50,000 times slower. Now, ZKSMT's running time for all these benchmarks is in the range of about 2 seconds, but the slowest ones here for cheesecloth would take more than a day each. Let's talk about some related work for ZKSMT now.
Well, maybe some more questions.
Yes.
So what did cheesecloth do significantly different than you?
Well, cheesecloth is a general purpose ZK protocol for executing any program
I see.
in zero knowledge.
I see.
So it has to be extra versatile, and accommodating that extra versatility in ZK means you need a lot of extra padding to hide what you're doing.
So maybe another question. So I guess we just talked about how the cryptography has really high overhead. Like bullet stuff is supposed to be relatively efficient in terms of the circuit. Like where in the cryptography does the overhead come from?
Well, it's from the most costly operation within our specific setup is multiplication. Although the very fact that we're doing cryptography at all means that it has to be a lot slower. Than what it would take to do in plain text.
Of course. But so the most expensive part is doing the multiplication gates in the volley.
Well, at the lowest level, yes. But there are also some other sources of slowdowns within ZKSMT that are specific to our protocol rather than just the commitments set up in general. So, for instance, list padding. We did some examination of list padding for what happens in our proofs, and we found that in a lot of our proofs, list padding was about 90% of the list entries in total. And also, one thing that turned out to be a big time sink within ZKSMT is the process of type checking that we need to do for proofs, because that means we need to fetch every entry of the expression table once. We need to fetch every entry from the table of lists exactly once. And when 90% of those entries are padding, that's a lot of extra cost.
Okay. Interesting. Yeah. Yeah, we can talk more about it later. Thank you.
All right, so ZK-Pi is a concurrent work to ZKSMT that is a ZK protocol for validating proofs made in the lean interactive theorem prover. The target domain of ZK-Pi is similar but not identical to ours. For ZKSMT, we target large proofs made of first-order rules, but ZK-Pi targets smaller proofs made of second-order rules. Also, cheesecloth is not the only general-purpose ZK protocol there is, but other general-purpose protocols suffer from the same performance issues that cheesecloth does. This is the case because general-purpose protocols need to model memory operations, and ZK read-write memory is much more costly than read-only memory is. ZKSMT uses read-only memory, so it doesn't have that issue, and also it's specialized to the task of validating proofs. Now, going off our results from ZKSMT, you may be wondering whether our design principles for our proof VM are generalizable, and whether we can extend it to cover ZK verification in other domains. And the answer to that is yes. We can provide co-inductive proofs of regular expression equivalence in zero knowledge. Yes?
One question. So when you give this, what does your zero knowledge simulator look like? I'm just curious.
Zero knowledge simulator for ZKSMT?
Yeah.
So we have the proof itself set up as a collection of tables. We have the table of proof steps, we have the table of expressions, and we have the table of lists. And to validate a proof, the verifier iterates over all the steps in that table, confirming that each proof step is valid in isolation. And then there are also some extra high-level checks that the verifier needs to do, like type checking.
So I think the answer to your question from the cryptography standpoint is that what they do, right, they want to prove some statement and they design the statement very carefully and design like the circuits that proving the statement very carefully. And really what the simulator look like, it's just a simulator for volley. Like there's a simulator for volley for any circuit. So it just happens that they put in a particular circuit. Does that make sense? Yeah.
All right. Questions?
So the simulator, what is it leaking? What is the protocol leaking here?
So the information leakage that happens within ZKSMT is the size parameters for the proof. We leak the total number of proofs, the total number of proof steps, the size of the expression table, the max length of a list within the proof, and also some extra size parameters. And along with that, we leak the number of uses of each distinct proof rule, but not their ordering relative to each other.
Yeah, thank you.
So, yes, for the new target domain that we consider, we're moving on to the domain of regular expressions, which are a common formalism for defining string patterns. More specifically, we're interested in the problem of regular expression equivalence, where we say that two regexes are equivalent if they have the same language. That is the same set of strings that they accept. This is an interesting problem because even if two regexes are equivalent, it's possible that one of them is safer or more efficient to evaluate than the other. And if we have a regex equivalence proof, we can use that to establish that some optimization for regular expressions preserves the semantics of a larger program that uses those regular expressions. Now, one reason why regex equivalence is a relevant problem for software development is that the use of these slow or unsafe regular expressions can lead to serious harm in practice. In 2019, the company Cloudflare suffered a 27-minute global outage because of a regular expression within their code that had an exponential running time on certain inputs. The reason why this was possible is that the standard approach for checking whether a regex accepts a string is to convert the regex into a non-deterministic finite automaton, or NFA, and then to evaluate the NFA on that string. Now, NFAs allow for unlimited branching during evaluation, so it's possible for an NFA to run in superlinear time and even exponential time on specific inputs. To see an illustration of this, let's look at two equivalent regular expressions, A star, and A star. They both accept any number of repetitions of A, but A star has a denial of service vulnerability that A star does not. The reason why this is the case is that if we have two consecutive A characters, for A star, we have multiple options for how to process them. Starting from V1, we can consume two A's by moving to V2, then V3, then back to V1 twice over. Or we can move to V2, then consume an A, staying at V2, then move to V3 and back to V1 to consume two A's. And whenever we have two consecutive A's, we need to explore both of those paths. And if we have two more A's after those two A's, both of those branching paths will branch again for more possibilities. And that leads to exponential growth. On the other hand, the state machine for A star has only one state and one path, so it has no opportunities for branching. The reason why this branching is problematic is that even though to accept a string, we only need to find one good path through the NFA, if we want to confirm that a string is rejected, we have to check every path through the NFA to confirm that it does not end in an accepting state. And if we give a string that's a lot of A's followed by a B to A star, we have more than 1,024 paths to explore because every branch goes down more branches every time there's another pair of A's. And we can add more A's to the front of this to make the denial of service attack as bad as we want. On the other hand, for A star, there's only one path we need to explore no matter how many A's there are in this string. Yes?
You can always make the running time to be length of string times the NFA size.
Well, there are ways to optimize on this. And for instance, there are DFA based regex string matching algorithms that avoid attacks like this. But the fact of the matter is that without this naive version is still the most common string matching algorithm in practice. Sorry, was there another question back there? Oh, no. So suppose that we want to prove that these two regexes are equivalent to each other. If we wanted to use a standard solver to do that, we would convert them into state machines and then reason about those state machines. But we don't want to do that because we're doing ZK proofs here. And all reasoning in a ZK proof needs to be explicit. That means that if we used state machine conversion, we would need to provide evidence for the correctness of our translation from one format into another. And we prefer to avoid that layer of indirection by reasoning about regular expressions indirectly. There's also a more pragmatic reason why we don't use state machine conversion or standard solvers, and that's that existing solvers have only limited support for providing proof certificates about regex equivalence. The solver Z3 is complete for regex equivalence, but it's only complete when it's asked to return a Boolean answer rather than a proof certificate that provides evidence of their equivalence. It does have a proof generator for regex equivalence, but it only handles simple cases and it's not complete.
Wait, so why do we want to show the equivalence of two regex? I don't know how that comes from your motivation.
So if we need to reason about regular expressions within a program, we'd be able to prove that. Or if we want to reason about the language of a regex in general, we could frame it as a regex equivalence problem. Or to show that one regex's language is contained in another regex's language.
So maybe you want to optimize one reg expression into another, and
yeah, but
need to validate they are the true equivalence.
So why would you need to do this in zero knowledge though?
Well, if the regexes are part of a private program.
Okay.
And well, even if the regexes themselves are not sensitive IP, you'd want to hide what they're doing within a larger system.
I see. Okay.
So CBC5, the other mainstream SMT solver, is not complete for regex equivalence, even when you don't ask for a certificate. It has some rewrite rules for simplifying regular expressions, but they're not a complete calculus for proving equivalences. Also, SMT Interpol, the solver that we use as a backend for ZKSMT, does not support regular expressions at all. Now, there is a reason why existing solvers are deficient in this regard, and that's that regex equivalence is a p-space complete problem. That means that the task of validating a proof that two regexes are equivalent is asymptotically just as costly as finding the proof in the first place. They can both take exponential time. And that means that for most purposes, there's no real benefit to having these proof certificates since it's just as easy to find the proof yourself. However, when we move into the domain of ZK proofs and we have to deal with privacy concerns, we do have a reason to value the ability to validate these regex equivalence proofs because we want to hide the regular expressions that we're proving equivalent to each other. To address that need, we introduce a new ZK protocol named CRAPE, which stands for Cryptographic Regex Equivalence Proof Engine. With CRAPE, the prover can demonstrate that it possesses a proof that two regular expressions are equivalent without revealing the proof or the regular expressions. As you can see here in the pipeline, the prover owns two private regular expressions and offline uses a proof generator to create a proof and then commits that proof to turn it into a ZK proof. Things then pass over to the verifier who validates that proof to confirm that it's correct. For that process of proof validation, we use a proof VM like the one we had for ZKSMT. And the proofs that we validate within our proof VM rely on a new custom calculus of proof rules, where we reason out regular expressions directly instead of converting them into state machines. Our proofs rely on two main constructs: regular expression derivatives and co-induction. Informally, derivatives are a way of modeling the changes that happen in a regular expression's behavior as it reads characters from an input string. And co-induction is a proof technique for modeling the cyclic patterns that arise in regular expressions behavior. Let's start by talking about derivatives. If P is a regular expression and C is a character, then the derivative of P with respect to C, written like this, is the regular expression whose language is the set of all strings S such that P accepts CS. For instance, the derivative of ABC with respect to A is BC. The derivative of AB or AC with respect to A is B or C. The derivative of BC with respect to A is the empty set. BC doesn't accept any strings that start with A, so the derivative has to be empty. It's also possible for there to be cycles in regular expressions derivatives, as you can see here at the bottom, with the derivative of A star with respect to A, which is just A star. Reading one A off the front of an input string doesn't limit the number of further A's we can consume with A star, so the derivative just loops back to itself. And once we have a definition of the derivative laid out for individual characters, we can generalize it to a definition of multi-character derivatives, which are just chains of single-character derivatives. Before we talk about a different proof technique that isn't adequate for our purposes, what we call the match rule. There's a result from prior work that says that if two regular expressions agree on the empty string and also all of their corresponding one-character derivatives are equal for the whole alphabet, those two regular expressions themselves must be equivalent. Now, match would let us prove equivalences between regexes in some cases, but it doesn't give us the completeness result that we want. The trouble is that we have to recurse on proving that these derivatives are equal to each other. And derivatives, as we saw before, have no guarantee of making progress toward a terminal base case because they can just cycle forever. That means that an inductive proof technique like match is not sufficient for our purposes. Instead of inductive reasoning, we need to use co-induction, which is a proof technique analogous to induction for reasoning about potentially infinite data structures instead of finite ones. For induction, we start from a base case and build up to larger structures using an inductive step, but co-induction works in the opposite direction. We construct a bi-simulation between two infinite objects to demonstrate that they continue to uphold some mutual property after any number of reductions. For our purposes, the two infinite objects are chains of regex derivatives. The mutual property that we want them to uphold is the absence of counterexamples, and the reduction is movement along these chains of derivatives. Co-induction is more appropriate for our purposes than induction is because, as I mentioned before, derivatives have no guarantee of making progress toward a terminal base case. That's why we need to think about chains of derivatives as potentially infinite objects. And we can take advantage of cyclic patterns in these derivative chains to establish our bi-simulations. Now we've talked about the idea of co-induction. Let's talk about our specific use of it within Crave. We construct bi-simulations by searching for matching cycles in the derivatives of the two regular expressions that we're comparing. And when we find a matching cycle, we start the construction of a bi-simulation between them. And we gradually construct that bi-simulation by excluding parts of the search space of potential counterexamples until we've covered everything. We're building up our assertion that there are no counterexamples in the search space of potential counterexamples. And once we've shown that there are no counterexamples anywhere, that's sufficient to say that they're equivalent to each other. The new sync predicate that we introduce here is what functions as a marker of incremental progress toward the construction of that bi-simulation. Because when we have a sync predicate, that means that we've excluded part of that search space from consideration. We gradually merge all of those parts together until we've covered the whole space. If we want to see a proof like that in action, we can return to our example regular expressions from before and prove that they're equivalent by identifying matching cycles in their derivative chains. The derivative of A star with respect to A is this regular expression, which then maps back to itself when we take the derivative with respect to A again. And A star is its own derivative with respect to A. We use co-induction to prove that those two align on any number of repetitions of A, and then we work backward from that to confirm that our two starting regular expressions are equivalent to each other. Now that covers the semantics of our proof, but we still haven't addressed the question of how we generate these proofs in the first place. Now, we can't use standard solvers, as I mentioned before, so we need to construct them ourselves. And we can take inspiration from this algorithm, which comes from existing work. This is an algorithm for checking whether two regexes are equivalent based on their derivatives. This algorithm takes two regular expressions, P and Q, as input, and it searches over the trees of their corresponding derivatives exhaustively until it finds a cycle on every branch in that tree. And if it manages to search over that whole tree without ever finding any counterexamples, we report that P and Q are equivalent to each other. The reason why we can stop searching when we hit a cycle is that if we hit a cycle on a branch, we know that if we keep going further down that branch, we'll just keep seeing more repetitions of the same behavior. So we ignore those cycles, effectively turning the infinite search space of potential counterexamples into a finite search space. That's the same reasoning that we use behind our co-induction rules, where we start a bisimulation when we find a cycle and then exclude portions of the search space based on those cycles. Now, this algorithm that you see here is guaranteed to terminate because there's a result from prior work that says that the derivatives of a regular expression must fall into a finite number of equivalence classes. That guarantees that we'll hit a cycle eventually on any path through the tree of derivatives, since every one of them has to fall into an equivalence class, and with the pigeonhole principle, infinite things have to fit into finitely many, will get overlap eventually. Now, this algorithm, as you see it here, only returns a Boolean result about whether P and Q are equivalent, but we can turn it into a proof generation algorithm that gives us those proof certificates that we want by effectively recording the execution trace of this tree search as a proof tree. Every time we have a branching case where we need to explore more derivatives, we turn that into an application of our co-induction rule. And every time we have one of those terminal cases where we hit a cycle, we turn that into an application of our rule sync cycle that starts the construction of a bisimulation. Now, we also want to validate these proofs in zero knowledge like we had for ZKSMT. And we want to hide the structure of our proofs, and some of the same techniques that we used for ZKSMT carry over to CRAPE as well. For instance, we set up our calculus of proof rules so that every individual step can be validated easily in ZK. They require only constant or linear time to check, and the operations that we need to perform for rule validating are just simple pattern matching or multi-set operations. However, we do introduce some new security measures that were not present in ZKSMT to hide more information. One of these is multiplexing. When we're validating an individual proof step within CRAPE, we run multiple checking instructions on that step, only one of which is for the real rule that step uses. And only one of those checking instructions needs to return a positive result, namely the real one. And importantly, the verifier can't see which one is the real one because the Boolean results from those individual checkers are committed. And multiplexing lets us hide the frequency distribution of our proof rules within our proofs and not just their relative ordering as we had for ZKSMT. When we apply multiplexing, we group our proof rules into three separate categories for the sake of efficiency. We put all the linear time proof rules in one category. We put the three most common constant time rules in their own category. And we put all other constant time rules in a third category. The division of constant time rules is just a performance optimization, but the important division is the one between linear time and constant time rules, because we prefer that we not turn fast constant time checks into slow linear time checks through multiplexing. There are also some soundness and completeness guarantees that we have for CRAPE that we should discuss. For our proof generator, we know that any proof that our algorithm generates is valid, and that our algorithm will successfully generate an equivalence proof for any two equivalent regular expressions. For the proof validator, we inherit some soundness and completeness properties from ZKSMT. Only valid proofs can pass validation modulo some negligible probability of our commitment scheme failing, and also valid non-cryptographic proofs can always be translated into our format, provided that we have support for the theories used. For our evaluation for CRAPE, we test both our proof generator and our proof validator. And the benchmarks that we use come from Flash regex, which is an older tool for generating regular expressions that are not vulnerable to denial of service attacks. We have 1,494 regular expressions, and we group them into more than 1 million pairs to check for equivalence. From those pairs, we identify 5,818 pairs of equivalent regexes that we can use for our testing. To test our proof generator, we attempt to generate proofs for all of those equivalent pairs. 3 of them hit our time limit of 10 minutes, but all the others succeed for proof generation, as you can see here. We have some slow outliers for proof generation. The slowest one takes about 500 seconds. But in general, proof generation is a quick process and only takes a few seconds per benchmark. Also note that these proof generation times include not just the proof search that I showed off before, but also some post-processing to remove duplicate steps from proof so that we can have the smallest proof that we want for validation later. Also, even though we have slow running times in certain cases, we don't consider that a problem overall because this is a process that happens offline. It's not a source of information leakage because the verifier isn't observing it. Moreover, regex equivalence is a piece-based complete problem, so slow running times for certain inputs are inevitable. To test our proof validator, we select a subset of those proofs from the first part and use them to test our proof validator. And we run the proof validator with 3 different configuration options for multiplexing. We use the default settings with the 3 categories that I mentioned before, and we also test it with no multiplexing and full multiplexing. No multiplexing means the only checking instruction run on a proof step is the one for its real proof rule, and full multiplexing means we run all checkers on all proof steps. No multiplexing makes things faster at the cost of reduced security, and full multiplexing provides higher security but worse performance. The median running time ratio of no multiplexing to the default is 0.77, and the median ratio for full multiplexing is 2.8. That means that turning off multiplexing does provide a performance improvement for us, but overall it's comparatively speaking not that large. So we consider the security gain that comes from multiplexing worth the cost. Moving on to related work, there are older ZK protocols that reason about regular expressions, but they only check whether an individual string appears in a regex's language rather than comparing 2 regexes to each other. Regex equivalence is in a higher complexity class than string matching is, so we can't reduce regex equivalence to string matching to use these tools instead. Also, all problems in p-space are solvable in zero knowledge by reduction to quantified Boolean formula solving, but we choose not to use QBF solving for CRAPE for the same reason that we choose not to use state machine conversion. We would need to provide evidence for the correctness of our translation from one format into another. We're also not the first to apply co-induction to clean algebra. Nate Foster et al. Have a paper about proving equivalences between netcat programs using co-induction. Going back farther than that, Foradini et al. Have a calculus of proof rules for proving bisimulations between regular expressions without doing state machine conversion. However, in that work, there's no accompanying decision procedure for generating proofs in the calculus. And on top of that, neither one of these papers does anything in ZK. To wrap up now, let's talk about some potential directions for future work based on these tools. An extension for ZKSMT would be the creation of a full ZK program verification pipeline that proves that a compiled binary corresponds to a private high-level program, and also proves that verification condition generation is done accurately for the final correctness proof that ZKSMT validates. As it is now, ZKSMT covers only the safety proof that comes after those 2 tasks, but in principle, a protocol similar to ZKSMT could handle those other parts. To improve CRAPE, we could extend it to handle clean algebra with tests, which are a generalization of regular expressions, and also features that are not allowed in pure regular expressions, like intersections and complements, and back references, and look-ahead assertions. Of course, performance optimizations for both tools are always possible as well. To summarize, our contributions are that we introduce the first protocol for zero-knowledge SMT proof validation, and for it we create a generalizable proof VM structure that we can extend to new domains. We extend it to handle regular expression equivalence proofs in zero knowledge, which makes that the first practical ZK protocol designed to target a p-space complete problem. And as part of that, we introduce a new calculus of proof rules for proving regex equivalences, along with a decision procedure that generates proofs in our format. If you want to discuss my research with me further, you can reach me at this email address, john.kolesar@yale.edu. Thank you.